All right, one more problem, and then I think we're going to leave this section here. The problem this time is from, section D, which says, suppose that I have a finite group G. Copy this down. And I have two subgroups, H and K of G, with the property that their orders M and N are relatively prime. We would write Mn equals 1 or GCD Mn equals 1. Then the claim is, or the thing to prove, is that H intersect K consists of only the identity element. And to prove this, I start with a little bit of a lemma. It's kind of an observation more than a lemma, but it warrants getting written down and spelled out, which is that the intersection of two subgroups is a subgroup. And the reason is because they both contain the identity. We can see that that's by definition. They have the same operation, and they're individually closed under their operations. So if I have two elements in the intersection and I multiply them, then the multiplication lives in each of them because they're individually closed. But if it lives in each of them, then it lives in their intersection again. And similarly for inverses. If you have an element in both of these groups, then since each of them contains their inverses, they each contain the inverse, and therefore the inverse lives in both of them, so it's in the intersection. So with this in mind, then, we are beginning to see a little bit of a proof strategy here, where H intersected with K is a subgroup of both H and K. What that means is the order of H intersect K divides the order of H, and the order of H intersect K divides the order of K. But we just saw the assumption was that the greatest common divisor of M and N is 1. So the only way that this can happen is if H intersect K is a group with just one element. And the only way to be a group with one element is to consist only of the identity, because every group has to contain the identity. And so that's as small as, there's not any way to be a one element group other than this, right? You'd be forced to be bigger. And so we're done. There are a whole bunch more problems of this type in this chapter, some of which are in the homework. And also in the homework is a whole slew of problems of the form classify groups of order n for n small. Like I think they do 6, 8, 10, maybe they do 12 also. I can go take a quick look. They got 6, 8, 10, but not 12. 6 and some of them we know how to do also because there's some prime numbers in there also, like 3, 5, and 7, and so on. And so this is a relatively thorough investigation of which kinds of classifications are possible for small orders. At this point in time, I want to take just a moment and tell you a little bit about sort of the point of all of this, since this was a short video anyway. The first thing is that, it's reasonable to want a full classification, right? Like you'd like to be able to say, I have a finite group, here's what I know about it, and then like look it up in your metaphorical dictionary of groups. To my knowledge, this is still very much not possible. However, there are a few things that we know. We know lots of groups of small order, where small here for humanity means like with computers and stuff, it means a lot more than small by hand. By hand, over my time doing math, I've had to classify groups up to order, I think, 59. 60 is a special number because it has three prime factors and one of them is repeated. It's 2 times 2 times 3 times 5. What you're seeing in exercises like this and the previous one is that prime numbers are your friend, and having a small number of small prime factors makes it pretty easy to work out what's possible in the group. So that makes groups of order like, 6 pretty doable. Groups of order 8, well, 8 is a power of 2 and 2 is a small prime number, pretty doable. 9, pretty doable, and so on and so forth until 60. 60, things start to get difficult. And so I've never seen a full classification of groups of order 60, and I'm sure there are many of them. But humanity has classified like all kinds of groups, and I'm not even going to venture to tell you how far we've gone. I know that there's computer software out there, things like GAP, that work in Maple, if my memory is correct, that are extremely proficient at classifying groups. But we don't know all of them. The purpose of these exercises is to give you some sense of flavor of how you go about figuring out what can be said about a group. So if you're ever doing math, for example, in a subsequent class, and you encounter a group of order 24, probably whatever information you have about it is limited. Maybe it comes from geometry, so you know how certain symmetries work. Or you know that it has to be order 24 because of some kind of combinatorial reasoning. Or maybe an abstract theorem tells you that there's some limitations on how big it can be. So you only know at most some kind of bound. You want to start leveraging the information you have because ideally you'd like to know everything about the group. And so the purpose of these exercises is to show you what kind of information you can deduce from partial information, like the size of a group or the properties of certain subgroups. And so there is so much that one can do with this that it's kind of hopeless for me to tell you everything there is to know. And so I've set aside a bunch of problems of this type, some pertaining to just working out subgroup properties, some pertaining to specifically classifying groups of small order. On the other hand, the problems in Pinter, the classification method takes some steps. So the only one that I've assigned for homework is the one for groups of order 6, because that only involves basically 3 steps. And so it's pretty doable. But one of the best things that you can do to study for the final, I know it's crazy to a little bit to be talking about our final exam for this class, but let's put it out there since it's on my mind, is practice classifying these groups. And you can do this partly by looking at other Pinter problems from this chapter, but you could also just like try to ask your own questions. Like personally, I don't think that I would have thought of this question, like I don't think I've encountered this before in my mathematical life. But I do think it's reasonable to say what can be said if I have subgroups with these properties, that they're relatively prime. Well, maybe you just look for examples where this happens, right? See if you can reverse engineer new examples of groups, maybe from their group tables, for example. And in this way, you will start to build up more and more intuition for what's possible with groups. All right, I got one more problem I want to show you guys, but I think this video has gone on long enough now, now that I got our little study pro tip out there. And so we're going to do that, and then we will be ready for our practice quiz.